Good morning, ladies and gentlemen. Welcome to the Indian Space Association SpaceTech Expert Talk webinar series. I'm Wing Commander Satyam Kushwaha, and I'll be your moderator for today's session on unraveling high-resolution thermal data from space, principles and application. We have an enlightening 120 minutes ahead of us. Our distinguished speakers will guide us through the fascinating world of high-resolution thermal data from space, both the principles behind this technology and its wide-ranging applications. We are honored to have with us today two experts from Suhora Technologies. First, we have Mr. Prathanu Maiti. He is working as a project lead at Suhora. He has been working on solving various geospatial problems with synthetic aperture radar, image acquisition planning, tasking and analysis, thermal remote sensing, optical satellite image processing, photogrammetry, and spatial analysis, and he's also involved in the assessment of customer requirement and making appropriate technical offerings. Joining him is Sarunisha R, who works as product lead for Suhora's next-gen ISA product with a foundation in computer science and engineering and a master's in remote sensing and GIS with specialization in geoinformatics. With a deep passion for problem solving in the defense sector, he is dedicated to advancing defense strategies through spatial analysis and intelligence gathering, ensuring precision and effectiveness in critical operations, contributing to shaping a more spatially informed world. Throughout the session, I encourage all attendees to use the Q&A function for any questions. We will address as many questions as possible during our dedicated Q&A segment. This is a unique opportunity for all to engage directly with leading experts in thermal remote sensing and its applications. Now, I would like to invite Lieutenant General A.K. Bhatt, retired, Director General of the Indian Space Association, to deliver his opening remarks.
Good morning, everyone. On behalf of the Indian Space Association, I warmly welcome you all for this 6th SpaceTech Expert Talk webinar. Today, we are focusing on unraveling high-resolution thermal data from space. What are the principles and applications? The field of high-resolution thermal data from space represents a frontier of immense potential for Earth observation and for space exploration. As we strive to enhance our understanding of our planet and beyond, thermal remote sensing offers a powerful tool to achieve these goals. Thermal imaging from space has applications across a wide range of sectors, from agriculture, urban planning, to environmental monitoring and defense. It provides us with unique insights into temperature variations on the Earth's surface, helping us to track everything from urban heat islands to forest fires, from crop health to industrial activities. Recent advancements in satellite technology and data processing have dramatically improved the resolution and accuracy of thermal data from space. However, fully leveraging this technology requires a deep understanding of both its principles and its practical applications. Today's webinar, we explore how we can harness the power of high-resolution thermal data for various scientific and commercial purposes. Our distinguished speakers, Prathanu Maiti and Sarunisha R, have extensive experience in geospatial technologies and product development, and are uniquely positioned to guide us through this complex landscape. They will shed light on the current state of thermal remote sensing, the challenges in data processing and interpretation, and the exciting opportunities that lie ahead. I would encourage all of you to engage in this dialogue. Your insights and your questions will definitely make the understanding of this subject more richer. Thank you, and I look forward to an enlightening session that will undoubtedly expand our knowledge of this crucial space technology and its practical applications. Over to the speakers.
Good morning, everyone. My name is Pratunu Maiti. I'm working as a project lead at Suhora Technologies. First of all, I would like to thank you, Indian Space Association, for inviting us to present this webinar. And also, I want to thank all participants for attending this webinar. And I also want to express my thanks and gratitude to Suhora Technologies Private Limited for giving us opportunity to speak today. So the purpose of this webinar is to unravel high-resolution thermal data from space. So generally, we use spaceborne imagery every day in Google Maps. But there are other types of spaceborne images exist, like radar image, thermal image. So each has its own unique properties. So far there are some spaceborne thermal imaging system are there, but those are very coarse resolution, which is not very useful for detecting small scale activity. So in this webinar, we will explore how high resolution thermal data can help to detect small scale activity. So this is a very important slide which shows the uniqueness of thermal imagery. Basically, this slide shows three images over same area. The left one is the optical image, middle one is a radar image, and the right image is thermal image. So basically, optical image is very intuitive to
Hello.
us. It shows.
Good morning.
Hello, sorry.
Yes, sir. I have joined. I have asked.
Okay. So optical image is very intuitive to us. It shows the outsides of structures during the day. And the radar image, of course, it can see day and night, and it can penetrate cloud. It can show the outside of structure during day and night. But the unique property of thermal image is that it can detect activity within the structure by measuring heat emission from the structures. So that's the uniqueness of thermal imagery. So let me start with this webinar objectives. So we will talk about the principles of spaceborne thermal imaging. Then we will look at some challenges in spaceborne thermal imaging. Then we will introduce spaceborne highest resolution thermal image. Then we will talk about what is the science behind the interpretation of thermal image. Then we will touch some use cases in economic monitoring, environmental and climate applications, and defense and intelligence applications. Then we will talk about the role of artificial intelligence in thermal remote sensing applications. So now I'm going to talk about the principles of thermal imaging. So basically, all objects above 0 Kelvin temperature emit electromagnetic radiations. Therefore, all the features we encounter in landscape every day, such as vegetations, water body, grass, bare soil, paved road, built-up area, emits electromagnetic radiations. These electromagnetic radiations are measured by sensor onboard satellites, and then thermal images are formed. So amount of emitted thermal radiation depends on its object temperature and material properties. So the top image shows basically the thermal remote sensing, demonstrate the idea of thermal remote sensing, and the bottom picture showing the thermal infrared portions of electromagnetic spectrum, which is 3 to 14 micrometer region. So all objects on the Earth surface emits electromagnetic radiation in 3 to 14 micrometer region. But those all 3 to 14 micrometer region is the emitted electromagnetic radiations. But all wavelength cannot be utilized for thermal remote sensing because certain wavelengths are absorbed by atmospheric gases such as ozone, water vapor, carbon dioxide. So this image shows the penetration capability of electromagnetic radiation through atmosphere. So the x-axis represents wavelength in micrometer, y-axis represents the transmittance. That means how well it can penetrate to atmosphere. So if you look at the 3 to 14 micrometer region, which is thermal infrared region, from 5.5 to 7.5 micrometer region, it is completely blocked by atmosphere. So this region cannot be utilized for thermal remote sensing. Generally, for spaceborne thermal imaging, 3 to 5 micrometer region and 8 to 14 micrometer region highlighted in red arrow are used for spaceborne thermal imaging due to their low absorption through atmosphere. So now I want to briefly talk about the history of spaceborne thermal imaging. In 1960s, the first spaceborne thermal satellite named TIROS launched. Then after 18 years, the first scientific thermal infrared system named Heat Capacity Mapping Mission by NASA launched. The spatial resolution was 600 meter. In upcoming 6 years, many advanced thermal satellites were launched. Then in 1982, 120-meter thermal imaging satellite was launched. The name of the satellite was Landsat 4. Then in 1984, the Landsat 5 was launched with same specifications. In 1999, two below 100-meter thermal imaging satellite were launched. The one is Landsat 7 with 60-meter resolution, and one is ISpA with 90-meter resolutions. So now I want to talk about the main challenge in spaceborne thermal imaging. So basically, spaceborne thermal image has very coarser resolutions. The reason is that relationship between electromagnetic energy with wavelength. So this equation tells this relationship. So where E is equal to the electromagnetic energy, H equal to Planck constant, C is speed of light, and lambda is wavelength. So energy is inversely proportional to wavelength. So shorter wavelength means more energy, longer wavelength means less energy. So this image shows basically demonstrate this idea using string wave analogy. So to create more waves on string, you need more energy. So this equation is very famous in physics because Einstein won the Nobel Prize for that. So these equations, these physics actually create challenge for spaceborne thermal imaging. So that's why thermal sensors have very large IFOV as compared to optical satellite. So IFOV means instantaneous field of view at a one single pass, how much area a satellite sensor can see at one instant of time. So this IFOV actually defines the spatial resolutions. So thermal radiations generally have longer wavelength because it has longer wavelength compared to optical wavelength. So due to this longer wavelength, it carry lesser energy. So to form thermal image, the thermal sensor need to measure sufficient energy to form thermal image. So to do that, thermal sensor increases its IFOV for recording sufficient energy. So that's why generally spaceborne thermal image have very coarser resolution. So if you look at any currently available spaceborne thermal sensors, Landsat 8, Sentinel-3, MODIS, ASTAR, ECOTES, all have very coarser resolution ranging from 100 meter to 1 kilometer. Then now I am introducing the spaceborne highest resolution thermal imagery. The resolution is 3.5 meter. So this is just a quick comparison between what's currently available spaceborne thermal imaging system versus this 3.5 meter thermal imaging satellite named HotSat-1. So the resolution of this satellite is 3.5 meter, and it is operated in 3.4 to 5 micrometer region of electromagnetic spectrum. So this is a visual comparison of what's currently available thermal infrared versus 3.5 meter HotSat-1. Location is Vizag, and the left image is optical image, middle one is 100 meter Landsat 8 thermal image, and the right one is HotSat-1 thermal image at 3.5 meter resolutions. So if you just compare these two thermal image, you can see that amount of detail present in that high resolution thermal image. We can see the individual roads, we can see different heat activity within the oil refinery. So very high detailed. So there is another visual comparison of dense urban area. The location is Las Vegas, USA. So you can see individual streets, building in that high resolution thermal image. So another visual comparisons over oil refinery. The location is Ruwais Refinery, UAE. So if you look at just high resolution thermal image, you can see different activity which was going on in that oil refinery. We can see the evidence of gas flaring. We can see different subtent level activity, and we can also see the thermal contamination from industrial facility. There is a just a quick overview of HotSat-1 thermal imagery. The resolution is 3.5 meter. It is operating in 3.4 to 5 micrometer region, and the sensitivity is 2 Kelvin. The scene size is 4.4 kilometer by 3.5 kilometer. It can take image at both day and night. It can penetrate smoke. That is also a unique capability of thermal infrared, and it can take image from 0 to 45 degree of nadir angle. So that increases its revisit capability over any point on the globe. So this is a nighttime thermal image over Fresno City, California. The image was taken on 24 October 2023. Basically, this image actually is color coded so that high area, bright orange areas represents higher thermal emissions, and the blue area represents lower thermal emissions. So this is not a temperature data. This is basically thermal emissions map. So that's the high resolution thermal image. So we can see individual streets, residential area. We can even see the different features inside airports, like airport runway, airport facilities, highway loop, cropland, etc. So this image actually shows the activity detection capability of high resolution thermal image. The location is Yokohama, Japan. The image was taken on 24 October 2023. And this is a daytime image. So we can see the vessel present in that image. We can also identify thermal contaminations. We also have see the power generation activity, also oil storage facility, and also industrial activity. So now we will go some places around the globe through the lens of this high resolution thermal image, and we'll see how detailed it can show us. The first location is Chicago, USA. The left one is optical image, and the right one is the high resolution thermal image. So we can see the very detailed heat signature around that place. So we can even detect the trends visible on the image. The next location is Suez Canal, Egypt. This is a nighttime image where fish farms are visible, bridge supports are visible. Also, a canal entering Suez is also visible. This is basically why this appearance of thermal image we will discuss later, but this is how the high resolution thermal image showing us the detailness. Next location is the water treatment plant over China. So the circular area indicates the water treatment plant. The image was taken on 21st October 2023. This is a very interesting image. The location is Al Jour Oil Refinery, Kuwait. Left image is optical image, and the right one is the thermal image over the same area. It's showing some thermal hotspots. So we overlaid these thermal hotspots over the optical image, and we have extracted insights from that image. So first of all, we have identified that thermal blooming from two sets of building flare plugs. We also detect subplant level activity. So thermal overlay on optical imagery can give us more insights. Later, we will look how a volcano looks in high resolution thermal image. This volcano is Kilauea volcano, Hawaii. This is very active volcano. So we can see in high resolution thermal image the thermal variation inside the volcanic crater. So image was taken on 8 December 2023. So now the next place is Mount Isa Mine Complex, Australia. This is one of the largest mine complex in Australia. Here zinc and copper operations is going on. So the left image over that area, and the right one is the 100-meter Landsat 8 thermal image. So now I am replacing this 100-meter Landsat 8 image with the high resolution 3.5-meter thermal image. Now we can see the amount of detail present in that image. So we can even detect different activity that was going on in that mining site. So we can see activity from leads melting operation, we can see power generation activity, we can see activity in slurry plates. So that give us better detailed. So thermal image can be taken both during day and night. But daytime thermal image completely looks different than nighttime image. So in this section, we will talk about the science behind the interpretation of thermal image. So why a daytime thermal image looks different than nighttime thermal image. So this is left one actually shows daytime image, and right one is the nighttime image over a location of Iraq. So you can see the river looks completely opposite. In daytime image, river looks blue, and right time image, river looks orange. Similarly, for other features, they also look completely different. So why is that? This is due to because the thermal properties of the terrain. So the thermal properties are the thermal capacity, that means how well a material can store heat. For example, water has highest thermal capacity. Thermal conductivity means how well heat can pass through a material. Metal can pass heat faster than rock. And then thermal inertia, how well material can resist change in temperature. Water has its highest thermal inertia. Thermal inertia is related to thermal capacity and thermal conductivity by the following equations. So due to these variations of thermal properties that lead to variations of thermal emissions of different material during a full day. So this image shows basically the thermal emission variations of different surface materials during a full day. So x-axis represent different times of the day, and y-axis represent radiant temperature. Basically, it's a measure of thermal emissions. So blue dot represent thermal emission variations of water, green vegetations, pink is most moist bare soil, and red represent metal objects. So water has very little thermal variation during the whole day as compared to bare soil or rock. Bare soil heat up more and at a faster rate during the day, and at night it cools also faster. So that's why it has very higher thermal emissions compared to its surroundings during daytime, and yet it has very lower thermal emission at night time as compared to water. Vegetation has so similar profiles like water, so it has very less thermal variation. So generally, water and vegetation has very less thermal emission during the day, and in night time it has very higher thermal emissions. So hello, and metal objects have no thermal variations at all. So this gives about the idea of how to interpret this daytime and nighttime thermal image. So again, the same two image over the same area, but now I have added the optical image one. So you can see rivers appears blue in daytime image, but in nighttime image it's appear orange. And on the other hand, bare soils appear orange in daytime, and in nighttime it appears blue. So that's the thermal properties of terrain features that leads to this difference appearance of surface features in both daytime and nighttime thermal image.
Can I ask a question now related to this slide, or we have to wait till the end of the presentation?
We can answer right now.
Okay, so
Yep.
Can you go back one slide before in the graph?
Yes. Yep.
Yeah, so the vegetation curve and the water curve, you said the variation is less. It's not like a huge variation what we saw in the bare soil rock.
Yes.
And now if you go to the next image.
Yes.
The next slide, yeah.
Yep.
Yeah. So why is that river color so drastically changed if that variation between that river was not really big? So the orange and the blue, there is a very big change in the color. So I'm just trying some hard time to understand if that variation was low, why the color difference is so big.
Yes. Okay. So whatever we see in that image, it is a map of thermal emissions. So water has little thermal emissions variation as compared to the surroundings. So if you look at the bare soil, it looks completely different in both two times, because it has cooled faster rate during night time and it's heat up more in daytime. So as compared to, this is actually a relative thermal emission scale. The temperature of a river does not change drastically. It is because of the appearance of surroundings, because surroundings has cooled at faster rate during night time. So that's why river have higher thermal emission during night time.
So is my understanding correct that the bare soil color on the top image, top right
Yes.
corner,
Yes.
is very reddish rather than orange, and the night time is like bluish. So the more reddish and blue, it means that there is more variation compared to the river, which is not reddish, which is orange. So we can interpret that it is having a less thermal variation. Is this understanding correct?
No, actually, this is not the variation map. This is basically if you look at the daytime image, this is basically map of thermal emissions. So if you look, so in that part of the image where their deep red is there, that means there is higher thermal emission. So this is this is higher thermal variations. This is all relative scale. This is not absolute. So water looks bright orange. That's because the emission from surroundings are very lower. So that's why
Okay.
it has higher thermal emission. It is all relative.
Okay, thank you. Yeah, got it. Thanks for the explanation.
Okay, so we can derive temperature from also thermal image. So whatever we see right now, it is a thermal image. Thermal image basically the map of thermal emission of objects, but this thermal emissions depends on object's temperature, atmospheric conditions, and emissivity, a property called material property. So here is a steps which can be used for converting thermal image to temperature map. So first step is the applying sensor calibration functions to thermal image for converting DN value image to recorded energy at sensor in watt per meter square. And the next thing, when we've done that, next thing is the atmospheric corrections. We looked at these thermal atmospheric sections. Some of the emitted radiation are absorbed by the atmosphere. So this mainly from ozone, carbon dioxide, and water vapor. So to measure correct temperature, we need to remove the effect of atmosphere. So there are available atmospheric codes such as ATCOR, MOTRAN, which uses data from satellite measurements like ozone, carbon dioxide, water vapor to correct atmospheric effects. And the last step is very crucial, which is emissivity corrections. To exact assessment of surface temperature, user need to correct emissivity from thermal image. So the impact of emissivity is that objects with exactly same temperature can differ significantly in their thermal emissions. So when we've done that, then we will get surface temperature.
What is the uncertainty percentage when you are calculating the temperature from thermal image?
It depends on a lot of conditions. First of all, it depends on how well we can remove atmospheric effect from thermal image. So availability of atmospheric data. Generally for atmospheric corrections, we take atmospheric gas measurement from satellite. So like
but can you give a ballpark number, like uncertainty is 5%, less than 10?
Almost plus minus 20% its accuracy.
Okay.
It depends on the main accuracy depends on these emissivity corrections. This is the main step. So I will talk about the concept of emissivity. Basically, the emissivity is a property of surface materials. Emissivity is the material property which defines how well a material can emit thermal radiation. So this image shows the impact of emissivity on surface temperature. This is a aluminium block having a single temperature 288 degree Kelvin or 15 degrees Celsius. 50% of the surface is painted black or 50% of the surface is polished. So by doing that, the emissivity is different. For painted black surface, emissivity is 0.98, and for polished surface 0.05. So thermal emissions from these two surfaces are measured by radiometer. So if you look at the radiant temperature values, from painted black surface, the temperature readings are very close to the actual temperature. But if you look at the temperature reading from polished surface, they're completely different, very much lower than the actual temperature. So this is the impact of emissivity on surface temperature. So this table shows the different emissivity of surface material, which is measured in laboratory. So water has emissivity 0.99, sand has 0.93, grass has 0.97. If you look at all metal objects like stainless steel, aluminum polished, or aluminum or polished metals, all have very less emissivity. So this image actually visually demonstrates the impact of emissivity on thermal emissions. So this image is taken by handheld thermal camera at air temperature 22 degrees Celsius. The image shows a handrail, a polished metal handrail bordering concrete stair, and a man holding it. So we can see the temperature of the human skin is around 38 degrees Celsius, which is correct. But if you look at the temperature of polished handrail and the metal ring, it is showing this minus 18 degrees Celsius, which is not possible because the image was taken at 22 degrees Celsius. So that's why we need to correct emissivity to accurately measure surface temperature. So this is showing the impact of emissivity on thermal emission over our 3.5 meter resolution image. The location is Dubai, United Arab Emirates. The right one is the hot set one thermal image. So if you look at the all metal surface, all have very higher thermal emission. This image is not emissivity corrected, so that's why this is appears like this. So all metal surface has lower thermal emissions because of these lower emissivity. So now I want to talk about some use cases of this high resolution thermal image. First, I want to talk about in economic monitoring. First use case is the power station, power generation activity. The location is the Yokohama Thermal Power Station, Japan, and the image was taken on 24 October 2023. So this circular area actually highlights some power generation activity, and the bottom right image actually is optical image corresponding of that area. So if you look at, there are 8 turbines, 1, 2, 3, 4, 5, 6, 7, 8. So if you look at the thermal signature of the 8 turbines, 2 turbines appear as a very bright orange compared to rest of the data. That means the turbine is on. And if you look at the other 3 turbines like this one, have very less heat signature. That means these turbines are off. And other 4 turbines appear in somewhere between, maybe they are active but not somewhat active. So turbine on-off status is visible. So we not only turbine on-off status is visible from this type of high resolution thermal image, also it helps us to understand power station operating capacity and infer power output and trends to time. So that's the capability of high resolution thermal image. So now we can see the activity monitoring of oil refinery over Jamnagar. So this rectangle highlights 3 chimneys. This is actually this 3.5 meter thermal image taken on November 30, 2023, where we can see 3 distinct heat signature from these 3 chimneys, indicating that 3 chimneys are active. So if you go to the next image, this image was taken by 2 weeks later. Now we can see two heat signature rather than 3. So that means 2 chimneys are active. So we can detect even chimney level activity from this high resolution thermal image. So now the another economic monitoring use cases is the fall detection or solar farm. Here is a large solar installations in Aragon solar area, Texas, USA. So left one is optical image, right one is the thermal image. So we can see the thermal emissions variations across the solar panels. So this helps to detect faults at a global scale, monitoring solar farms to detect potential faults on a global scale and at a higher frequency. This helps to reduce cost than current methods. So another economic monitoring use case is nuclear power stations. This image shows Kori nuclear power plant, South Korea. And this circular area highlights the hotter effluent water from this power station to sea. Of course, this is environmental concern, but from this hot effluent water, we can understand power output at key sites. So now I will ask my colleague Sarunisha to take over.
So yeah, thank you, Pratanu. And so I'll take on from here, and we'll look into detailed applications on the environmental and climate side. Followed by, so now we are in a position, and I think Pratanu has made it clear how you interpret this high-res thermal imagery, be it from daytime or nighttime. So now we'll look more into the applications, followed by how you can automatically extract information from them. So using AI and other approaches, how you get into extraction of these data. So one of the major studies that's around and the use of satellite imagery being utilized is monitoring climate change activities across. So how you can aid or support climate change and climate policies. So thermal contamination is one such phenomena that is widely happening because of the industrial outlets, and it deeply affects the marine life. So this 3.5-meter imagery can actually show us which outlet of certain industries actually are beyond or above the norms of the level of emissions that they create or outlet they create. So you can actually monitor those as well. So here you have an example of a Ruiz refinery in UAE, and here the circled area. So you can see the thermal, the water being inserted into the sea, and you can see the stark temperature difference between the actual sea surface and the water being let out. So these kind of monitorings help us assess whether or not industries and organizations are within the limits of emissivity or not. In the same area, to the left of the image, we can see gas flaring activity. So why is gas flaring an important concept? So it is a common practice across industries in the globe that you burn out byproducts that are coming out of these petroleum refineries and so on, and even other industries. So these are again major contributors to the greenhouse gases that we are talking of controlling and stuff. So this can also be done within the norms under the policies, or sometimes it's also an illegal activity. So monitoring these gas flaring emissions continuously across on an industrial scale can help you give an idea whether or not the certain country or industry is following the norms of flaring, etc. There is another use case. One is wildfire monitoring. So now this has become a very common climate change phenomena across the globe, wherein we are seeing a lot of wildfires happening. So the first thing that you can't, like when a wildfire happens, so you try to capture a large area image by optical, there is smoke, so it kindly it full-on blocks your vision. You can't see the hot spots. But when you go for a high-risk thermal, it penetrates smoke and heats. So now here you are able to see the hotspot of where exactly the forest is burning. So this was from the Northwest Territories wildfires in Canada last year in July. So we can actually see all the fronts of fire where are still burning. So now this you have a comparison image on the left, which is a Sentinel-2 false scar. And we can see exactly on the surface level where the hotspot is there and the fire is still open. And another common phenomena is the urban heat island. So we have widely seen land surface temperature images and equations being used for monitoring and planning and predictive plannings as well in the urban level. So this is of California, this image, and so you can see the dense heat signature that is coming up from an urban sprawl sort of scenario we are looking at. So this can also help urban planners differentiate between areas, whether there is a planned planning happening, the kind of heat emissions happening from that area, and when there is a urban sprawl sort of situation, the level of urban heat emissions happening. So this also gives an idea for environmental activists as well as urban planners to take into account the kind of emission that's been put out from a city. So this is another interesting use case of how it's one of reactive steps to controlling uh, greenhouse emissions or global warming scenarios across. So this was an collaborative project within Oppo Darwin and Satru's image for HotSat. So here what they have basically done is, so there is a night image that gives you an idea of the heat activity of that specific location. So now they use a canopy cover model and they find out it's called the tree stress model. And so there is this index that they are using called this tree stress index. So now when you have a layout of urban activity happening by a segmented image that is you're seeing on the left is from the HotSat image. And then you can see the canopy cover in percentage. With these inputs, you derive the tree stress index. So this tells you by planting trees at certain locations that you can bring down the heat emissions that's happening in that specific area of interest that you're looking at. So this is one way that you can counter react to environmental issues such as global warming and other stuff. Or even when you're planning a greenhouse or a more greener and planning is happening. So we can take these kind of models and this image can be a very good asset in those sort of plannings. So coming to the most interesting application of this high-res thermal imagery. So as we all know, when Pratham started it off the session, we know that thermal images were actually launched. So thermal satellites were actually launched as a requirement of strategic applications. So when there was a need to monitor strategic locations and activities, that also created a need to have a thermal spaceborne sensor in space. So we'll walk you through some of the defense-based applications that can be done from this image. So this is a nuclear facility in North Korea. So this was in news and like recent news last year when the site was told to be shut, but then there were evidences found out being active. So here you can see there are two images. So one captured on 23rd of November and the other on 28th of October. So on the first image that's captured in October, you see there is there has been significant heat emissions happening on the marked areas. That is basically the outlet. So there's a pumping station. The larger part is the pumping station, and then there's a reactor located here. So on these consecutive images, you can see that on a certain day that there is being water pumped out of the station and also one of the reactor is active. There is a significant heat signature here. So these kind of evidences give you an idea into the activities of certain strategic locations, whether they are active or not, and this can also be done on on even a finer assessing level. So this is again from a nuclear facility, but from Houston. So here you can see the water cooling reservoir. So you can see that where the outlet is happening, the water is coming out comparatively in a higher heat. And as a principle of the cooling pond works, regulated to the right of you, the temperature is getting down. So you can monitor. So we have heard of this principle, but now you can actually visualize how a cooling pond reservoir actually works, and you can also see the stark difference here. So this is also it also gives you an idea of how much time it will take, consume to cool it down, or other kind of operational inputs and insights. So this is one interesting image wherein from this monument basically there are these flames that are lit on the stairs of it. So it's like a flame that keeps on burning. So it's a very small area, and from a spaceborne imagery, you can still see that flames active. So this, compared to the environment, is still you can see a fire event of so smaller scale still be captured from space. So this is a, I'd say, a proof of concept to the technology that even the smallest human activity can also be tracked from space or monitored from space. So as we talk of environmental causes and defense and intelligence cases, so wars and humanitarian situations are of prime importance. So this was captured on 29th of November, so in the Gaza Strip. So you can see hotspots of fires burning. So this is again a signature of, say, smokes coming out and active fires happening in the region. So this is also one of the ways in which you can effectively monitor actual ground-based events. You can see it for yourself if there's a fire or not, and how much damage a certain fire is causing, and sort of that stuff. So yeah, coming to the role of AI in this thermal remote sensing application. So whatever we have been seeing so far was based on interpretations, based on several experience. If you have a ground truth, a comparison. What if you want this to be automated on an operational level? Can it be done? And if yes, how is it done? Here, I'm very simple. It is in words. We just focusing on two things: what can be done, and where it can be applied. So, in general, when we talk about thermal imageries, the one thing that we focus on is activity, monitoring them. So, to monitor activities, that can be technically done in two ways. When you're talking about, say, machine learning models or any other automative statistical approaches. So, one is anomaly detection, and other one is feature extraction. So how detecting an anomaly will help in any of these cases, and the same way feature extraction, how it feeds and helps in this. So on your right, you see certain applications, that is agriculture, urban heat island analysis, wildfire, and energy efficiency. And the same way in defense and intelligence, we have activity monitoring. So these are several applications we are focusing on right now. So when we talk about anomaly detection, an anomaly is anything that is off the chart compared to your environment. So that's how we look in an image. If anything is off the threshold to the comparative background of the image, you call it an anomaly. So then we investigate the anomalies. So this can be done in a very basic level based on automated thresholding based techniques. So any kind of thresholding based models can help you figure out these anomalies in the images. But then when this applications can widely be used in agriculture applications when you're monitoring crop health or any other kind of emissivity which leads you or helps you to assess crop health. So thresholding based techniques are a good bet there, and there are various models starting from segmentation based to other thresholds. If you can say, a lot of VGG based models are widely used and proven to have a better accuracy in this part. Then we talk about urban heat island analysis. So how do you want to monitor this? So here you want a bit of anomalies with some agent-based rule sets. So here comes an additional idea of feature-based assets. So you monitor certain anomalies and you map them. You label them as certain agents of changes of higher emissions, lower emissions based on your understandings, and then that can also be used with feature-based models for urban heat analysis. Wildlife detection and wildfire detection monitoring, sorry, so they can also be done in the same way. So when we talk about feature extraction, so activity at different scales can also be extracted as features. So once you have enough data sets to say, okay, this event is how, so the interpretation, when you make sure that this, if I have interpreted this some way, if this comes out a certain way in the image, this is my feature and this marks this. So now these are rule-based agents. So we use a lot of rule-based agent-based analysis for feature extractions. So that is how you can monitor a lot of activities on ground, wherein you say persistent monitoring. So a certain place X looks like this, and anything that is above the threshold, so you extract that feature and you put on a rule about that. This needs to be marked as an anomaly. This tells me there is some sort of activity happening. You flag it as an event. There is an agent to it. So these are how automatic advanced deep neural networks are used to monitor activities on a automated perspective from AI. So one fine example that we have tested is this. So here you can see the port of Fujairah in UAE, and we can see there are certain ships on the jetties and they are being fueled. So object detection is always of interest when it comes to strategic applications. And when we generally talk about object detection, there is a requirement of large levels of data. So there is optical, there is SAR, and then you come to thermal. So what does thermal give you more that optical or SAR doesn't, or it's not able? It's something that's an USP of thermal, if I have to say so, is that you can classify the detected objects based on their activity. That is not something that can be done in, say, an optical or a SAR-based images. So for the detection parts, as we have talked about segmentations, we have talked about feature learnings. So you detect the model, and now based on the features of how it appears on your thermal image, can tell you a lot more about the kind of activity that object is part of right now. So if you look at this zoomed out image of these three ships that are docked in the jetty, that you can see there's a significant different heat signature on this one. So the claim is it's either it's being fueled, it's a tanker. So basically it's a tanker, it's a tanking area. So they are being fueled. So this gives you an idea of what if whether the ship or the vessel I'm looking at is laden or not, what kind of good it's carrying. So this helps a lot in strategic applications of monitoring illegal shipments, transshipments, and even dark shipping. So when some AIs of yours fails and tells, I'm not laden, the ship is not laden, or this is a dead ship that's just abandoned in the sea. But a thermal image overhead can tell you whether that ship is actually laden or not. Even if it's laden or not, how much of quantity, you can make estimates out of it further. And also tell you more about dead ships, which is a common practice of a common malpractice in the maritime domain. So when there is a significant heat signature to the object that you're looking at, you for a fact can tell that there is some sort of activity, and definitely the ship is not a dead ship or something that's just there out in the sea. So these kind of further assessments and classifications can help you well more, or this acts as a trigger and further fact analysis for more strategic applications, that is operational workflow. And in general, when you're working on automated AI-based applications for thermal, they serve as a very good trigger for any strategic monitoring. So if that is a regularly monitored site, you want to know what kind of activity is happening out there. If you have a nighttime image over a desert, say, and there is some sort of thermal signature that you can see, you can for a fact say there is some sort of activity happening there, which can again not be monitored by a optical or SAR, because they are going to give you asset-based information. So thermal stands has a added advantage on giving you activity-based understanding of what you're looking at in the image, and the I'd say the scale at which it's happening also, because being a 3.5 meter image, it gives us a good understanding of the scale at which it is happening. So you can monitor from something like a campfire to a activity happening at an industrial scale. So that is one when you talk about this applications. Other than this, we also saw some use cases on solar farms. So a thermal image that's ground-based thermal has always been used for equipment investigation. So spaceborne thermal images at this resolution can also help you investigate electrical equipments on a solar farm level. So you can try and understand which of my equipments are functioning in the right way they are supposed to, and which are not, the anomalies that are happening there. So this is one of the applications on the industrial segment if you have to look at it. So yeah, I think we are done. Yeah. So thank you. So this was from our side. Open to questions now.
Yeah, thank you, Sarunesha and Pratani. We have a couple questions in the Q&A box.
Okay, we'll just get to that.
I think the first question is from Mr. Alagu Raja. What are the sources of HR thermal images?
Okay, so basically this hotset one launched by SatView, a UK-based company last year. but it operated for 6 months, but due to some communications failure, it is no longer able to take images. So right now, we can not able to task any image, thermal image, but in mid 2025, next year, they will launch HotSat 2, the next version of HotSat 1. So they will provide the same type of data, 3.5 meter thermal image. So.
Right. Thank you for that. If anybody has any more questions, they can raise their hand or open their mics for the same.
Yeah, yes, thank you. I have one question. These industrial application images which were showed, do you have any example where a brine discharge is coming out of a desalination plant and that anomaly has been detected?
Can you please repeat your question?
Yeah, regarding the industrial images which were just shown,
Yes.
like for an LNG facility and flare and that sort, I am asking about any example which is related to brine discharge coming from a desalination plant. Do you happen to have any sample of that?
That depends on this was activities going on or not in that particular capture of particular image acquisition time. So
Maybe not pretty sure if we have it over a desalination plant, but then yeah, we do have these samples over several other industries.
So
yeah, the reason I'm asking is that we have some environmental concerns about the brine discharge, whether they are following the rules regulation which comes out of the desal plant. So I'm just thinking that if this tool what you have or this HotSat images can detect this kind of anomalies.
So as a matter of theory, yeah, that's what we're trying to say. From the sample, you will be able to understand that it can definitely detect that if there is a significant difference in temperature of the water being let out from that plant. But if it's be like specific over the area, we will have to look if we have over a desalination plant. But yeah, by theory, yeah, it is quite possible. Yeah.
Okay.
Yeah, we have another question from Mr. Raju. What are the ways to get maximum resolution thermal images freely available for educational and research purposes?
So right now the freely available thermal image is 100 meter, which offered by Landsat 8. Also, as there is a sensor on board Terra satellite named Aster, which also provide 90 meter thermal image. But freely available, the thermal image is the up to 90 meter. So below that, there is no currently available any thermal image. So freely.
Mr. Arvind, you can go ahead with your question.
I just want to ask, what is the cost of one scene of this 3.5 imagery by SATVU?
Right. Actually, they were in a commissioning phase. They not disclosed any price informations. So
I think maybe we can discuss this on the mail or something.
Okay. No issues, no issues. And what is the likelihood of this HotSat 2?
In next year, in mid 2025.
Okay, and I just want to answer the previous question that desalinization one, that yes, it is very much possible because these people, Suhora must have not taken the images of this thing, but then certainly this and anything which is activity based thing happening, it is possible by thermal imaging. There is absolutely no issue.
The difference is high enough, so it can easily detect.
Yes, it can be done.
Yeah, we have a technical question from Mr. Sivakanda Swami. What if a country is trying to spy the other country through its thermal imaging technology? Wouldn't they try to hide that by covering the infrastructure using material that can be penetrated? If so, what is that material?
So, I mean, sorry. So, if you're talking about materials here, okay, what I understand from this question is, okay, if somebody is looking at your facility and you want not to disclose it, so you looked at that image that we showcased of that nuclear facility in North of Korea. So That's pretty much heat signatures. So camouflages is a concept wherein you try and hide your assets by covering them up with some similar material or something that is doesn't we call them adversarial patches. So you use them to cover your assets with some combination of depending on the material you're using. So that's a different aspect of one. And when you're talking about thermal, it's all about heat. If there is a significant heat in the atmosphere, because it's being captured from it's being captured from space. It's a space-borne sensor. So if there is significant heat out of any activity happening and it's being picked by a space-borne sensor, it's sufficient enough. So it can be captured and you can just make it out there is some sort of activity. But then to the part of being hidden by something, that comes in a different context.
So any material basically who trap the heat emitted by objects, so that can hide the heat signature in that image.
That's one way of doing it. But it's too large to be covered.
Right. Next question, what is the maximum spatial resolution we can go for Wi-Fi application? From Ms. Shushmata.
So generally for wildfire applications, generally we need a high swath width image, high imaging area. From this type of sat views high resolution image, the scene size is very limitations. So we can see the 16 square kilometer. It is will be not useful for large scale wildfire applications, but it will be helpful for small fire anomaly detections and in very local scale. So the high swath width would up to 100 meter, maybe 50 meter resolutions, it will be enough for large scale wildfire monitoring. But right now, this is not available with that specifications.
I'd like to add a few comments on what has been stated. One was on this question of the spying aspect and can it be hidden? When we do image analysis from identifying activities in a certain area, we do not rely on a single source of data. If you see the electromagnetic spectrum, there's a set of energies that we measure, monitor, analyze, and then use that to predict the nature of activity that is happening in a certain area. Now, thermal energies are very good for identifying and locating things which are especially deep and buried because of the ventilation systems. For Team Suhora, I'll request that maybe in another future presentation, if you end up doing, we should look at much more microscopic, granular, say, analysis of a certain area like Gaza. The way you showed that image, you were showing, say, 2-3 fires. It was giving as an image impression to a third person that this place is totally decimated and only 3 fires are there. But if you take a much more deeper analysis of it, then you will find a lot of variations because there are a lot of houses where probably people will still be residing or things of that nature. So you will get a much more interesting variation in that. Second aspect that I wanted to bring out is that the 3 to 5 microns in which the hotsat is operating is in the reflected radiation. It's a reflected energy. Whereas when you get into the 8 to 14 micron, it is a radiated energy. So there is a huge, so analysts who use thermal data, they need to be, when they make their inferences, they need to keep these aspects in mind. Otherwise, there could be some sources of error that can come into analysis. The third aspect that I wanted to find out, mention is this was a specific question on this water effluents that are going into the sea. So whenever we do some kind of analysis of this nature, we need to understand the time series operations of this specific maybe place or maybe other effluent plants as to how they are operating of a similar nature. Because what happens is when the churning and all takes place, it causes a change. Now, if you see something for the first time instantly, yeah, it may show you a variation, but it could be because that all other plants of this area, of this particular nature, could be giving a similar signature. So when we look at certain things, we should also look at other aspects from the, say, hyperspectral side. We should also look at it from the electro-optical side, measure turbidity and those kind of aspects, that actually what is happening on ground. Otherwise, sometimes in terms of, in an urgency, we can make some critical errors. Urban heat islands, yes, it's a very, very interesting thing, and it has huge applications for the real estate industry, I would say, because let's say Gurgaon, if you see the city of Gurgaon, the way it has come up, there are severe challenges of urban heat islands, and which cause severe diseases as well as deaths for specific people who are below the poverty line, because in low wind, hot, humid conditions, there it causes challenges of that nature where people fall ill, and the deaths in India are not recorded as those attributed to heat. And these challenges become very, very interesting when we are promulgated with those heat wave map, heat wave warnings that come up in India. So that is another area for public good that probably Suhora could work upon and bring out. This is something interesting. Next, important aspect that we need to keep in mind is that when you are doing daytime thermal and when you are doing nighttime thermal. Now, daytime thermal is reflected energy, as I mentioned earlier. Whereas when you're doing nighttime, it is pure radiation. So this is something which probably maybe we could have it another day, but when you're doing fingerprinting of buildings and all, it will be very interesting, and you will find those variations coming up, especially when you're, say, studying cities and places of work. For example, what are the human occupancy in buildings? So, when you want to study a city, daytime, yes, most offices are occupied, but there are a lot of places which are occupied during nighttime. Now you want to study how the traffic flow will happen in evenings, or which are the areas, how that area should be developed because there is a nighttime activity happening there. So even in terms of urban planning, those things can come into play because you will need some kind of a eateries outside in those places. So those are commercial places where same technology can be deployed. From a military perspective also, like any military, when it operates, you need cookhouses. Now, cookhouses are something which give out heat. So they are very, very good sources of detecting human activity suddenly happening in a jungle. And, we have this problem of foliage penetration. Foliage penetration is ability to detect things which are happening below forests. They become very, very difficult to detect. So from a national security perspective, or in that case, especially in thickly covered forests, thermal activity integrated with ELINT activity can give you very, very interesting outcomes to detect where probably something fishy is happening below the forest in areas where they're not supposed to happen. These are some of my comments. I just thought that they may help the audience here. Thank you so much.
Yeah, we have a couple of questions more, Saranisha. So what application is used to convert raw pixel value of thermal sensor to construct thermal image? From Mr. Suresh Kumar.
So generally for urban heat island applications, also for volcanic modeling, generally for volcano activity forecasting, there is a additional layer of thermal layer. So that we need that the exact measurement of temperature. So whatever we see for that example, Kilauea volcano, this is only the raw pixel values, just the visual thermal emission map. But to fit into in thermal forecasting model, so we need exact assessment of temperature. So there is another use case for converting this raw pixel to actual temperature measurement.
Right. There's another question. Can you explain specifically the role of thermal resolution in urban forest development. Remote sensing.
Can you explain specifically?
Can you hear me?
Is it urban forest development?
Or some plantation?
Yeah, I think it's related to the stress, heat stress mitigation techniques you were talking about during the city planning.
Okay. So, so the role of it. So basically, if you're like, there is a lot of planning that goes into, before you have planned cities. There are urban planners who look into things. So you have mesoscale models for all the cities that are going to be constructed, the smart city concepts. So when you're planning, rooftop covers for your planned cities, or high-rise buildings, or green covers for your buildings. So there is a quantum that you arrive to a number ki how many plants or how many acres of vegetation needs to be there. So this was in relevance to that, wherein a city route was modeled to identify where there is too much heat emission, and increasing the vegetation at which point will smoothen out, or say even out the level of heat emission across the city. So this can also be planned. So this is part of can also be a part of urban planning when you're planning smart cities. Okay, so if this is my layout, and if this is the amount of vegetation that needs to be there, so you have multiple ways in which you can have this vegetation cover in an urban area. So maybe you can just pick out points where having them can actually reduce the amount of emissions, or regulate your heat flow within the city and improve air quality and factors, etc.
So this slide shows actually this example of this use case, the minimizing heat stress. Basically, SatView provided HotSat1 data to this OPO. OPO converted this HotSat1 thermal image data to heat stress index, and they also used multispectral images to detect canopy cover, and they combine using heat stress and canopy cover, they derive T stress index. Due to this using this T stress index, they have identified some areas which can be plantation can be done to minimize heat effect. So this is another use case which each basically have been done using this thermal image. So here in this image, red has areas basically shows where plantation needed.
Yeah, another question is any challenges in scanning in hotter summer months, especially during daytime when ambient temperatures can reach up to 40 degrees and above? How accurate is anomalies detection as the ambient and object temperature difference is very minimum? They on mute.
Mute. Mute.
No, it's
Okay. Okay.
You want to take that answer? Is, but again, it's related.
So you can start.
So, okay, so this is specific. So this has to be a case that we have to test. But then again, as we discussed initially, the way the image gets captured, it's a relative scale. Though the minimal difference is going to be less, but then there is a scale to that specific scene. That the scene is not constant. The scale is not constant. Sorry, the scale is specific to the scene. The temperature at which the highest that's captured on the scene to the lowest on that scene. That is how you put the low and high scale. So it's a relative scale. So even I understand the fact that in this specific condition, the subdivision of that scale is going to be it's going to be a smaller scale, but then it's still going to have a colder end and a hotter end. So maybe that's how you can, because we don't have an exact example at this exact precise temperature, answer that.
So I want to just add, even during these 40 degrees temperatures, if you take picture of any oil refinery, so if there are very activities going on like gas flaring, maybe plant level activity, and if you can take also example this mining area where concentration activities, melting operations, also activity from slurry pits. So this can be easily detected because temperatures anomaly is quite enough to detect those events. So it depends also the temperature of the objects and its difference with a background. So yeah.
Another question. You explained that these instruments operate in 3 to 5 nanometers and above, but material like lead can't be penetrated with those wavelengths. What if the country cover or made the facility walls with lead mixture?
So first of all, these should be 3 to 5 micrometer, not nanometer. Not understood that. It cannot be penetrated.
So we're saying if the material is lead in itself and it can't penetrate. I don't think if it's 3 to 5 micrometer.
Can you please explain this part? Who raised this question? Material like lead cannot be penetrated with those wavelength.
We can come to that question later, Pratanu. We have another question.
Okay.
Can drones be used effectively?
Just be deliberate and loud because they're not understanding the question. They're trying to read.
So they're also reading. Can drones be used effectively for capturing thermal images? And what is the best resolution we can have?
Yes, generally drones are used for inspecting faults on solar farms. Generally, images can be up to 1 meter, maybe 50 centimeter, 20 centimeter. But the main challenge is drone is the coverage area, and you need more cost to a survey using drone as compared to satellite image. But in the single image, you can cover more area, and yes, at a global scale, you can detect faults.
So yeah, just adding to that. So most of the applications, when I was discussing the role of AI, when the models we were talking about, most of them, they have been trained on UAV-based images. So there are sufficiently available airborne images, thermal images available for training models, and so the challenge is actually having something at a close to a meter or less than 5 meter from spaceborne. So at that scale, you already have significant amounts of UAV based and drone based images. So I think we have very good resolutions out there, and some data sets are even open for analysis and stuff. So as Pratham mentioned, most of them have been done for industrial scale monitoring of equipment monitoring and inspections. So this is one of the widespread application that this drone based imageries have been used for.
Are there any more questions? You can still raise your hands or ask it in the chat box.
We would like to thank, since there are no more questions, we would like to thank both our experts, Pratanu Maiti and Sarunisha from Suhora, for the wonderful presentation they have given. I think the understanding and of the availability of thermal from space and its disruptive applications need to be advertised more, because this is an area which will create huge disruptions in future in the understanding of Earth activities from space. And I'm happy that Suhora has taken the lead in India from space, and I'm sure that with their good analysis and some good articles, maybe they will work towards increasing public awareness about this technology, because it has wide-ranging aspects of technology. Over a period of time, people have got used to generally the SAR and the electro-optical dimensions of space. But thermal dimensions have their own unique value. And I think this was the last barrier of, I would say, remote sensing from space that was left, which is now getting breached. So I thank all our esteemed guests who had joined us for this fantastic expert talk. And I thank all of you for your patience and for your active participation. If there are any other queries, our esteemed members of this webinar can get in touch with us, and we shall try our best to answer the queries. And please keep looking out for our next event, which we shall be notifying in the public domain very soon. Thank you so much.
Thank you.
Thank you,
for
sir.
joining.
Thank you.
Thank you, Pratanu and Sarunisha. Thanks a lot. And
Thank you.
thanks to all who have attended the seminar. Most importantly, we would like a feedback from you. What would you have liked more in this presentation and in any expert talks which we hold in the future? Thank you.
Thank you. We are ending the webinar.